So this is just a short section on viscosity um, in laminar flow. So let me just briefly say, laminar flow is smooth flow. So if you look at just a big river where everything's sort of smoothly flowing in the same direction, this is a special type of flow called laminar. It's as opposed to turbulent flow, which is violent whitewater type flow, where the water is tumbling and mixing all the time. In laminar flow, the layers kind of stay where they are, and objects that are in a given layer just stay in that layer as they move as they move with the fluid. And so the physics of these two is different. And so we're really just going to talk about viscosity in laminar flow and smooth flow. And the way the viscosity is defined, viscosity is kind of like a friction for fluids. It's a measure of the friction. And so what this is a picture of is this is just a board or something, this black line here is a board sitting on top of a fluid. So this could be a metal board sitting on top of a layer of oil or something like that, or it could be a board sitting on the surface of water. But anyway, it's got some area A, and it's floating on top somehow. And it's being pushed by a force F at a constant speed V. And so you can imagine yourself just dragging a raft or something over the surface of the water. The force required, it depends on how fast you want to go. If you want to go faster, you have to push harder. And it turns out the formula for this is the force required to go velocity V depends on the viscosity, the velocity, the area. So if you have a big area, if your board has a big area, then requires a greater force divided by the depth. So the deeper it is, the easier it is to move the thing along. If you're really close to the bottom, it makes it harder and harder to move it. And that's because something called the no-slip condition. The liquid at the bottom of a surface, the liquid at the bottom that's in contact with the solid surface below is moving at speed 0, regardless of what the object is being dragged at. The water in contact with the stationary bottom is moving at speed 0. And so the farther away from you are from that, the easier it is to get the thing going to a velocity V. And so so this is the dependence. The force is equal to viscosity times the velocity you're traveling at times the area divided by the length. And so if you want to measure the viscosity, you can just measure the force, the depth of the water. This is the L, right? The velocity you're traveling at and the area A, and that will tell you the viscosity for a fluid. And so there are a few of these. I'll just write them down. Here's eta. Here, let me write them. So this is the fluid, and this is eta, and the units for eta is pascals times seconds. And so for air, it's about 0.018. Let me just do a few of these things. For water, this is at 20 degrees C. I'll just put these at 20 degrees C. This is 1.002. The viscosity is for water is very strongly temperature dependent. So it's 1.002 at 20 degrees C. At 0 degrees C, right before it freezes, it's 1.8. At boiling, it's 0.28. And so there's a great change in viscosity for water depending on its temperature. I was going to do oil. So oil, this is like SAE10, which is what you put in your car in the wintertime, maybe. This is at 30 degrees C. It's close to where your car might be operating. It's 200. So it's got a high viscosity. Honey is about 2,000 to 10,000. And so on. So you're getting some idea of what the viscosities look like. So here's an example. Is what force is required to drag a board of area 4 square meters, so 2 meters by 2 meters, right, over water at 0 degrees C. Again, that's liquid water. It's just, it's at sort of its maximum viscosity at 5 meters per second on a lake 5 meters deep. And so we just evaluate this. Here's the viscosity. We look it up at 0 degrees C. It's 1.8 Pascal seconds, which is Newton seconds per meter squared. Velocity is 5 meters per second. The area is 4 square meters, and the depth of the water is whatever that is, 18 feet or something like that, 16 feet. Fives cancel. I get 7.2 newtons. Meters cube. All the meters and seconds canceling, just left it with newtons here. The only thing that's a little tricky about this is I'm assuming laminar flow for this, and it may be that pulling something at 5 meters per second is going to make the flow less than laminar, and so it's possible that this solution, this equation, isn't applicable to this problem, but we'll just pretend that it is. And if you can drag it at this velocity and still not have too much stirring in the water, then the answer is 7.2 newtons. So you can look at the flow rate through a tube, and it's called Poiseuille's law. I think it's pronounced Poiseuille, so Poiseuille's law. He's a French guy. And if you remember, we used Q for the flow rate, right? Q is the area times the velocity, say. It's the volume per second. It's d volume, d time, right? And it turns out that the flow rate through a tube depends on the pressure difference at the front and back of the tube, right, if the flow is going this way, times pi r to the fourth, where r is the radius of the tube, over 8 eta L. And so we actually derive this formula in fluid mechanics, but you can just apply it, and we can just talk about it for a second. So this works in your veins, for example. If you want to pump fluid through a pipe of any kind, the flow rate you get is proportional to the pressure difference on either end of the pipe, right, times pi times the radius to the fourth power, we'll come back to that in a second, over 8 times the viscosity times the length. So the longer the pipe that you're trying to push it through, the lower the flow rate. And that sort of makes sense because you have to push it through more and more pipe. The higher the viscosity, the lower the flow rate, right? It's in the denominator. The greater the radius, the greater the flow rate, right? In a big way, right? A 10% change in the radius produces about a 50% increase in flow rate. A factor of 2 in radius, if you double the radius, right, you increase the flow rate by a factor of 16, right? Because it's to the fourth power. And so, when people are trying to improve the flow of blood in somebody's heart or their brain or anything like that, one thing you could give people is a blood thinner, and that reduces the viscosity. And so you can increase the flow rate by reducing the viscosity, and that'll help get circulation going better in somebody who's had a heart attack or something. But you can also give them a drug that that dilates their veins and arteries. And those things are much more effective because the increase you get here is to the fourth power. And so there are a lot of examples where you can increase the radius and have a much bigger effect than changing the viscosity.